Okay. Bismillah ar-Rahman ar-Rahim. Can you hear me, please? Excellent, excellent. Mechanobiological approaches to understanding orthopedic and dental implants, bone interactions, designing more efficient implants. In this talk, first, I will ask 2 questions. Then I will introduce biomechanics and one of its salient features, so-called bone remodeling process. Then we'll introduce some models on bone remodeling, including our own models and some of the projects executed in my lab, orthopedics and dental biomechanics lab at American University of Technology will be introduced. And finally, we'll make some conclusions. Let me ask dear audience, let me ask you 2 questions. On the left-hand side, you can see a screw inserted in a piece of wood. And on the right-hand side, please go to the next slide.
Next slide.
Okay, thanks a lot. On the left-hand side, let me repeat my point. I'm going to ask you 2 questions. The first question is as follows. On the left-hand side, you see a screw inserted in a piece of wood. On the right-hand side, you see a screw, so-called pedicle screw, inserted in a piece of bone in vertebra in order to fix deformity of the spine. My question for you, please. If the story on the left-hand side is the same as the story on the right-hand side, that's the first question. The second question, if we bioengineers are going to design orthopedic and or dental implants, should we design based on just mechanical principles or engineering principles, or we need to use mechanobiological principles? Oh yeah. Thanks a lot for sharing your points, dear professor. At the end of my presentation, you will, dear audience, you will have detailed answers to my question. What's biomechanics? Biomechanics actually aims to explain the mechanics of life and living. Everything must obey the laws of mechanics, from molecules to organisms. Please go to the next slide. Next slide. Yeah, thanks a lot. Everything must obey the laws of mechanics. This is the definition provided by Y.C. Fong, so-called founder of modern biomechanics. Based on this definition, I think that we biomechanists should be able to explain the abnormal shape of the trunk in this tree, in the figure you see, as well as we bioengineers should be able to explain the causes. Go and show the right-hand side of the slide. Please see this deformed spine. It's called scoliosis. We bioengineers, we biomechanics should be able to explain the deformity of the spine and the causes of the spine based on what we know from biomechanics. And we have to be able to find solution for this kind of problems. Okay? Okay, I didn't know that. Okay, go to the next slide, please. Okay, in a scientific meeting, dear audience, in a scientific meeting in 1987, two researchers presented results of their studies. One on the left-hand side, results of investigation on a crane which was designed by a Swiss engineer. Okay? The distribution of principal stress within the crane. And on the right-hand side, you see the distribution of a spongy bone or trabecular bone in the proximal femur, done by a German anatomist named von Meyer. Let me ask the audience, please, dear audience, can't you see similarities between the figure on the right-hand side and the left-hand side? The question is as follows. Can't you see some similarities between the distribution of the spongy bone on the right-hand side, trabecular bone on the right-hand side, and principal stress direction on the left-hand side in the crane? There are some similarities there, right? This was a basis for a revolution in bone biomechanics. After discussing about the similarities found between the right and left-hand side of the story, these two researchers came up with theory, so-called trajectorial theory, which states that a spongy bone or trabeculae are distributed aligned with the principal stress direction. They are not randomly distributed within the space. Okay, they are not randomly distributed. Another German anatomist took this theory one step further, and he stated that not only spongy bones are distributed along with the principal stress direction, but also if you increase the load applied on your bone, the density of your bone would increase. And if you decrease the load applied on your bone, the density would decrease. If you change the direction of load applied on your bone, then the direction of trabeculae would change. Please go to the next slide. Okay. You may ask, what's the reason? What's the reason for this kind of behavior? Because spongy bones are not distributed randomly in this space. Because bone is a smart structure. Bone is a smart structure. And in a smart structure, we have sensors and actuators. Here on the left-hand side, in the figure on the left-hand side, you apply load on a piece of bone. You can see osteocytes, mechanosensors. They sense the mechanical stimuli, then send appropriate signals to the actor cells, to osteoclasts and osteoblasts. Simply speaking, please look at the figure on the right-hand side. In the bone remodeling, we have bone resorption and then bone formation at the same spot. In your bones, we have resorption and then formation continuously from our birth to our death. If bone resorption is more than bone formation for a long period of time, please go to the next slide. We will experience osteoporosis, low bone density. So, in order to tackle problems like osteoporosis, we shouldn't expect that just people from the medicine side, from medicine should contribute. But we bioengineers should be involved, should get involved, should work in order to understand the governing equations for the bone remodeling process. Please go to the next slide.
Next slide, okay.
Next slide, okay. Would you please show the screen to me? Okay, okay. Another example which might be of interest.
That's better.
That's okay. You can show the screen, the big one, but not your laptop, please. Would you please show the screen, but not your laptop's screen? Okay. It was a tough day for me. That's okay. That's okay. Thanks, Prof. On the right-hand side, you see a dental implant inserted within a piece of bone. Okay. Every respected audience knows. Oh my God. I can see reflection of my voice, and is bothering my ears, but that's okay. Dental implants are much stiffer than its neighboring bones. So, based on what we know from bone remodeling, because of abnormal distribution of mechanical stimuli, in the vicinity of implants, we have abnormal bone remodeling. So the screws will be loosened after a while, okay? Will be loosened after a while. And on this figure on the left-hand side, as you're showing to me now, on the vertical axis, you see a rate of change of density of your bone. And on the x-axis, you see the stimulus, mechanical stimulus. If the mechanical stimulus is within the equilibrium zone, within the, thanks a lot. Can you hear me, please? Excellent. I assume that you can, okay. Please,
yes.
Please, okay, please make it mute because it's bothering my ears. Yeah. Okay, I'm going to continue. God bless you. God bless you. Thanks a lot. See, on the left-hand side, see, if the mechanical stimuli is within the equilibrium zone, then there is no net gain or loss of bone. It's beautiful, right? But if the strain or stress is greater than the upper limit of the threshold or equilibrium zone, you will gain bone, new bony material. So your bone will get stronger. And if the stimulus is less than the lower limit, you will lose bone. That's why we are advised to have continuous physical activities. And I do recommend all the respected audience to have regular physical activities at least 3 times per week in order to have a healthy bone. Please go to the next slide.
Okay.
God bless you. Okay. Based on my talk so far, I'm 100% sure that all dear respected audience appreciate that bone is an active, small part, and optimal structure. It's beautiful. It's extremely small. One way to describe our bones is that they are actually dynamic structures which can gain maximum strain with minimum mass. On this slide, you see in the middle, if you apply load on bone architecture, because we have sensor cells within the bone, the sensors, so-called osteocytes, they sense the mechanical stimuli, then they send appropriate signals to bone-making and bone-destroyer cells, osteoblasts and osteoclasts. So we can have a fight between the destroyers and builders. If builders activity is more than destroyers, then you will gain new bony materials and your bone gets stronger. Okay, please go to the next slide.
Okay.
Okay, mechanobiology. This is a beautiful story. There is an interplay between mechanics and biology. On the figure in the bottom of this slide on the left-hand side, okay, you see a fractured bone, okay, a fractured bone, and that region almost in green is the fractured side. If we apply load on this piece of bone, fractured bone, and we look at the fracture side, the cells there experience mechanical stimuli, let's say stress, strain, and based on the stress and the strain, they send appropriate signal to other kind of cells. And these cells can be differentiated into appropriate kind of cells. If the mechanical stimuli are suitable to make cartilage instead of bone, these cells will be differentiated into chondrocytes. If you need bony material and the stimuli are suitable to make bony materials, these mesenchymal stem cells will be differentiated into bone-making cells. And on the right-hand side, also you can see a description of mechanobiology. On x-axis, let's assume x-axis, you have a strain. On y-axis, you have relative velocity of the fluid phase with respect to solid phase within the tissue. And the third axis is the time. Depending on the value of a strain and the relative velocity of fluid, as you can see, as time goes on, you can see different kind of materials produced during bone formation process. Please go to the next slide. I'm going to explain about some of the theories that we have suggested related to bone remodeling. One of the most rigorous mathematical models proposed on bone remodeling was made by Hovin and Hegedus in 1967, so-called adaptive elasticity theory. In their theory, they've assumed that rate of bone remodeling is a function of volume fraction and deformation gradient. But based on what we know from bone biology, we know that bone cells, bone actors, bone-making cells and bone-resorbing cells, they are working at the interface of the solid phase and voids. So instead of volume fraction, we have suggested a new parameter, so-called free surface density, SV. SV is equal to the area of cross-section between the solid phase and void over the total volume of your bone. And after some mathematical manipulations using continuum mechanics, we came up with a new formulation for the remodeling, which states rate of change of apparent density is a function of free surface density and stimulus.
Dr. Gholam, this is Dr. Zuhair Marmar. We are very sorry because we are a bit late and we have committed to another lecture at after 2 minutes. So please, we are very sorry, but you have to stop after 2 minutes. Thank you very much.
Thank you, Doctor. I appreciate it. Okay, let me summarize my talk. Another model that we have suggested is by considering microcrafts. Go to the next slide, please.
Next slide.
Next slide, please. Yeah, another model that we have suggested, and this is another model, unfortunately, I cannot explain because of the lack of time. Please go to the research philosophy in ODPL. Go to the next slide.
Next slide, okay.
Go to the next slide, please.
Come on, okay.
Oh, yes. My philosophy in research is through understanding mechanics of biological tissues and the structures, we aim at decreasing pain and increasing the quality of life. Please, to the next slide.
Okay.
Go to the next slide.
Okay.
Yes, one of the theories we have suggested on bone resorption and some other works. Let me make concluding remarks. Would you please go to concluding remarks? Please, next
slide.
next slide, next slide, next slide, please. Oh, yes. No, go back. Yes, biological materials and tissues adapt their structures based on the mechanical and biological conditions. So we have to understand mechanics as well as biology in order to be able to find solutions for problems such as osteoporosis and osteoarthritis. A new generation of orthopedic and dental implants should be designed based on mechanobiological principles, but not just pure mechanical laws. And next slide, please.
Okay.
As we can see in the Holy Quran, it says, Allah subhanahu wa ta'ala, Bismillah ar-Rahman ar-Rahim, وانظر إلى الإذام كيف ننشزها ثم نكسوها لحما فلما تبين له قال أعلم أن الله على كل شيء قدير. After almost 20 years of working on bone remodeling process and theories, I'm always amazed by this sophisticated structure. Please, next slide, Professor.
Okay.
Next slide, the last slide, please. Professor, the next slide. Yes, I would like to appreciate many graduate students and many different universities I was privileged to work. Thanks a lot. I'm sorry. Thank you.
Welcome.
Thank you.
د.غلام, we are very pleased to have you in this conference. Thank you very much for joining us. We are looking forward to continue and maybe doing some research together. We are very, very thankful for you. Thanks a lot.
Thanks, Professor. The same feeling here. I do appreciate your kind invitation. The same feeling here. God bless you. Thank you.
Goodbye, Doctor. We are permitted to go to another